Hello! Today we'll talk about forward and deferred rendering, or let's say shading. These are methods used to render objects in the world in any 3D software. So you'll find forward deferred rendering in any software, not just for games. Why do we have two different passes for rendering objects in the world? Because we must understand that light is what makes an object visible. Lighting gives the object a 3D look. Some areas are bright, some other areas are darker, so shadows, reflections, all these concepts are related to the lights. For example, if we look at this object here on the screen, it may appear a 2D, but when adding some lighting layers, it becomes 3D. So each triangle or pixel on the screen must know which dynamic light affect it and the normal direction, material properties, and why I mention dynamic lights and not static lights? Because static lights are basically just textures. When you choose static lights, press bake lights, you are actually generating some textures, or let's say light maps. These light maps are added an extra layer on top of your materials to make them look like they have shadows or lighting. So static lights are lighter on performance but heavier on memory. Dynamic lights, however, must be calculated every frame, and this impacts performance. That's why we have two rendering paths. Each has its own way of dealing with lights. So the question here is, do we calculate light for every object separately? And this is the forward rendering. Or store informations about the geometry in the screen, and then at the end we add lighting only to what is visible on the screen, and of course this is deferred rendering. We talked before about passes in the GPU pipeline. Vertex shader, rasterization, pixel shader, and we have the output. And there is also the pre-pass, where the engine generates the Z buffer, and the Z buffer is used for occlusion to know which objects must be rendered, etc. So the Z buffer is important for all later passes, and it's actually the easiest to calculate because no pixel shader there and no colors added or is required. So we need to start with the Z buffer. Then comes to the base pass or the main pass. This pass creates colors. It looks different depending on whether you use forward or deferred rendering. And also there is other passes between pre-pass and base pass depending on your features and depending, of course, of your engine. So now, after preparing the Z buffer, we face a problem. How we deal with lighting? The way we calculate lighting, we will decide the performance. So in forward rendering, we calculate lighting for every object separately. I go into each object and I say, for all lights that affect you, calculate them. So the complexity of the mesh is connected to the lights and also the number of triangles. Okay, we will see that later. And in the deferred rendering, we first render all the meshes and draw them into a group of images called G-buffer. So every mesh on the screen stores informations into this buffer. What we have is an image that contains a data of those models that we will be used in the next few passes. So basically, we transfer our meshes into images. This means that in every frame, a set of images created, each one stores information we will need in the later passes. For example, one image for normals, another image for shadows, another for reflections. So a group of images will be used by the GPU to calculate lighting only for what is visible in that image. Meanwhile, in forward rendering, we handle each object one by one. For each object, we do everything, then we move to the next one, and so on. So now, let's talk about forward rendering, but in the base pass. As I said before, the base pass that renders the geometry or the object, this is the main difference between forward and deferred rendering. In the forward rendering, the lighting is calculated directly in the base pass. So for every object, or let's say for every pixel in that object, we must read the vertex attributes, identify the materials, apply all the lights that affects this object, and finally, we've got the final image, which contains all the colors and everything we need for this object. That means, in the base pass of the forward rendering, we get one full image and not just multiple images like we will see in deferred rendering. So how does this happen? Every time there is a draw call, the geometry is sent through the pipeline. The vertex shader runs, then rasterization, then the fragment shader, or let's say pixel shader, and finally it is sent to the screen. And we go to the next draw call, the next draw call, and so on. So with each draw call, the system calculates lighting inside the pixel shader and sends the final result to the screen, which is our frame buffer. So the complexity, or let's say the difficulty of forward rendering, depends on the number of objects in the world that are affected by lights, the number of lights themselves, and the complexity of geometry. For example, if you have a high poly model with many triangles, the lighting here will be much heavier than if you have a low poly model. In both methods, forward and deferred rendering, static lights are always calculated. They are always handled by the base pass. Why? Because, as I said before, they are just images. In the end, the engine only adds an image, let's say the baked light map, on the top of the 3D model that contains shadows and lighting, etc. But they are completely static. So in the base pass of deferred rendering, we don't calculate dynamic lighting. Instead, we write surface data, informations about the surface of each pixel, color, normal, roughness, metalness. All this data is written into something called geometry buffer or G buffer. The G buffer is not one image, it's a group of images that store all these informations, every important detail about the surface, anything that will later affect lighting is stored into these buffers. Later in the lighting pass, we will read the G buffer to understand the properties of the surfaces and to know how light should affect them. So in the base pass of deferred rendering, we will still use the full pipeline, but here we don't have lighting. It's only writing the data into the G buffer, and these G buffers are used later in, let's say, these multiple images like G buffer A, B, C, etc. are used for lighting. This process is called MRT, or multiple render targets, and it means that in one rendering pass, we don't produce just one render target, but many images at once. And remember, we have more than 4 G buffers, sometimes even up to 10 in a single frame. Now imagine in 60 frames per second, so many images created again and again. This consumes a lot of memory, or let's say VRAM, and also a lot of bandwidth. Why bandwidth? Because every one of these images has the same resolution as your game. If you play a 4K, then every single G buffer is a 4K, and there are multiple of them, so all the time the data moving between VRAM and the GPU pipeline, cache, and so on. That means deferred rendering is very heavy on the bandwidth. This is why 4K at 60 FPS is so difficult, and it's not about VRAM size, it's all about how much bandwidth the GPU can handle, because the bandwidth is actually the most common bottleneck in modern GPUs. To summarize, for the base pass of deferred rendering, we will still run the vertex shader and pixel shader, but lights is not calculated here. Instead, surface informations is stored to multiple G buffers, and later in the lighting pass, we will use these buffers to calculate the final lighting for the screen. So now, after the base pass in deferred rendering, we move to the lighting pass. Here, the lighting is not calculated per object, instead it's calculated by reading from the G buffer. That means the lighting system uses the G buffer data to understand all the surface properties and then applies lighting to the final image. This is very different from forward rendering. In the forward rendering, lighting is calculated per object and actually per triangle of that object, but in deferred rendering, lighting is calculated per pixel of the final screen image. This gives us a big advantage. In deferred rendering, the performance does not depend on the number of objects in the screen. No matter how many objects you have, the cost of lighting will stay the same because the system is not calculating the light for every single object. It only cares about the resolution of the screen, for example, 4K, 2K, etc., is what decides the performance. So in deferred rendering, the complexity depends on how many pixels are affected by lights and on how many lights you have. Meanwhile, in forward rendering, the complexity depends on how many objects there are and how complex their geometry is, triangles, polygons, etc., and how many lights affects them. Now, let's talk about shading models. So, what are shading models? They are the rules or methods that decide how lighting interacts with a material. Most of the time we use PBR, physically based rendering. This means we have the standard material values, normal, base color, roughness, metalness, etc. These are the basic values almost everyone uses for materials. This is what we call PBR. But sometimes we need different shading models. For example, lighting does not interact with hair or skin in the same way it interacts with a simple PBR surface, for example. So in that case, we use another shading model. That's why shading models exist, to define the way lighting is calculated for different types of surfaces. Now, here's the difference. In forward shading, shading models are easy. Why? Because we calculate lighting per object. So in every object, we directly calculate all its data. If the object mixes hair shading with PBR shading, there's no problem. We just calculate it right away. There is no need to store anything for later calculations, for example. But in deferred rendering, it is different. In the base pass, we write PBR values into the gbuffer, and if another shading model is used, we must also store its ID in the gbuffer. Later in the lighting pass, we read this ID to know how to calculate lighting for that shading model, or let's say that particular pixel. So the problem is the gbuffer has limited space. Imagine for every pixel on the screen, we must know which shading model is used. If there is too many shading models, there won't be enough space in the gbuffer to store all their IDs. For example, in many games, there are maybe 5 main shading models, or maybe 6, okay, let's say, but some games may need more than 5 or 6. Maybe sometimes we need more. This can cause problems for deferred rendering because the gbuffer cannot handle so many shading model IDs. That's why if you plan to use many different shading models, you should think about using forward rendering maybe. So one more important term here is BRDF, bidirectional reflectance distribution function. This is the function inside the shading model that tells the lighting system how to calculate light for that surface. For example, for PBR, the BRDF says this is how you calculate light for a PBR material. For hair shading, the BRDF says you can use this function to work with. For skin, there's another function, etc. So this is the BRDF function. So the lighting pass must always know the shading model ID for every pixel so it can choose the correct BRDF function. So in summary, forward rendering handles shading models easily object by object. Deferred rendering stores shading models in the gbuffer, but the gbuffer has limited space, which makes it harder to support many shading models. Now, let's talk about transparency. Transparency means objects like glass, smoke, particles, or similar effects. In forward rendering, transparency is handled natively because forward rendering work object by object. So when the engine renders one object, it calculates everything related to that object directly. This means it is easy to make an object transparent and also show what is behind it. We still need the Z-buffer to know what is the front and what is behind, but overall, transparent rendering is much lighter and much easier in forward rendering. In deferred rendering, however, there is no simple way to handle transparent objects, because in deferred rendering, we do not render objects one by one. We group them into the gbuffer, so the system cannot easily say this pixel is transparent, let's show what is behind it. Instead, we must handle transparency in a separate pass. We can choose that actually in the project settings, or we can play with transparent materials. There is an option there in the material also. Okay, I will mention that in the material section. Now let's talk about MSAA, multi-sample anti-aliasing. It's a method used to smooth the edges of each object, to remove jagged lines and make the image look cleaner. It is one of the classic and very effective techniques for anti-aliasing. In forward rendering, MSAA actually works perfectly. Why? Because in forward rendering and for every object, we already know the triangles, the pixels, and the final color. So the system has all the informations it needs to apply MSAA directly and create smooth edges. But in deferred rendering, MSAA actually is not supported because in deferred rendering, the base pass store only surface attributes in the gbuffer, such as normal, roughness, etc. So when we want to apply MSAA, we don't have enough information about final colors, so we can't compare and create some smooth edges. Okay, I will talk about anti-aliasing to know how our MSAA work, but We can actually say that MSAA is not supported by deferred rendering. Since most modern games use deferred rendering, they replace MSAA with TAA, temporal anti-aliasing, because TAA works differently. It compares the current frame with the previous frame and tries to smooth the edges by blending between them, but actually we don't have another solution. So let's talk about advantages of forward rendering. Perfect with transparency, supports MSAA, which is a very effective anti-aliasing method, makes it easy to use different material models and different shading models. Since lighting is calculated per object, you can freely use many models without being limited with the G-buffer space. Also, it's very good for low-end devices or weak hardwares such as VR headsets or mobile phones, because there are no huge G-buffer to store and no heavy bandwidth to use. Performance is easier to achieve. It was also the first rendering method ever created for games. At the beginning, actually, games used the CPU only, so CPUs did not have a VRAM, so calculations had to be done one by one. That's why forward rendering is the oldest and the most basic method, but actually it's used in a lot of games and still used right now because there is something called forward rendering plus, and it's actually very good with dynamic lighting because there is some clustering systems, etc. But actually still limited in Unreal 5, so we can't use it in the right way, but still very good for mobile games. There is some disadvantages of forward rendering because you can't use nanite. Because nanite only works with deferred rendering, and the cost of lighting in forward rendering depends heavily on geometry. If a model has many triangles, a high poly model, the lighting cost becomes expensive. Also, there is an overdraw. Why? Because sometimes the same pixel is calculated many times. For example, lighting may be calculated for one object's pixel and then calculated again for another object in the same screen pixel. This wastes performance. Forward rendering also cannot handle too many dynamic lights. Dynamic lights are expensive here. It works much better with pre-computed, or let's say baked lighting and shadows. If you are baking your lights and shadows, then forward rendering is a good option, but you will lose nanite and lumen if you choose it, but it's actually an option. Now let's move to deferred rendering, which is also an excellent for scenes with many dynamic lights, because lighting, as I mentioned, calculated per pixel from the G-buffer, not per object, and also work with nanite and lumen, which are modern Unreal technologies. And lighting here is handled per pixel, not per triangle, so performance does not depend on object count or geometry complexity, it depends on screen resolution. Also enable many screen space effects like SSR, screen space reflections, or deferred, decals, and other effects that depends on screen space data. It is the recommended method when your game has many decals, many dynamic lights, or relies heavily on nanite and lumen. There's of course a lot of disadvantages of deferred rendering because it needs a large G-buffer. Each buffer is the size of the screen resolution. As I mentioned, 4K, there's a 4K G-buffer, a lot of 4K G-buffers each frame. This makes it very heavy on memory bandwidth. And I mentioned the main bottleneck in modern GPUs is the bandwidth, not the VRAM. If your bandwidth is not enough, the frame rate drops. Transparency is more difficult to handle in deferred rendering. It must be handled with a forward pass. Shading models are harder to support in deferred rendering. The G-buffer has limited space per pixel, so storing many shading models is not easy. And of course, MSAA is not supported in deferred rendering. For VR games, forward rendering is usually the better choice. Why? Because VR requires very high frame rates, usually 90 frames per second or even more. Forward rendering can use MSAA, which makes the image much smoother for the human eye. It is lighter on bandwidth and more comfortable for VR players. Deferred rendering is in VR can be heavy, and without MSAA, edges may look worse. Okay, finally, let's talk about some practical notes. And deferred rendering on desktop or PC is different than deferred rendering on mobile. On PC, we use the standard deferred rendering system, but on mobile devices, a different method is used called TBDR, tile-based deferred rendering. And tile-based deferred rendering, instead of creating one very large gbuffer that uses the full screen resolution, which will consume a lot of memory and bandwidth, the mobile system divides the screen into tiles, or let's say small sections. For each tile, a smaller gbuffer is created. Lighting is calculated for that tile, then the system moves to the next tile, and then the next tile, and so on, until the full frame is complete. This saves memory and bandwidth, which is very important for mobile GPUs. Even though the method is different, the same BRDF function are used, and that means the way materials and lighting are calculated is the same, but the passes and data handling are optimized differently for mobile hardwares. Also, Nanite is not supported, as I mentioned, for forward. It only works for deferred rendering because Nanite does not render geometry the same way as traditional meshes. Instead, it divides the model into some clusters and assign ID for each cluster, let's say for a group of triangles, and then these clusters are processed to decide which part of the model is visible. After that, the base pass uses Nanite visibility data together with non-Nanite meshes to create the standard gbuffer to complete the deferred rendering pipeline that we know, and I will of course talk about it in the next video. So the main difference here is how Nanite prepares the gbuffer. Testing on devices. It is always important to test your game on the target device. Do not just optimize on your own PC and assume it will be the same everywhere. Why? Because tile size is different on different devices. For mobile, for example, bandwidth limits are different. GPU drivers behave differently, so you must always test on your actual hardware you are targeting. For example, if you want to release your game on mobile, should constantly test on real phones, you must have your target device. You must test on your target device to guarantee good performance. For the bandwidth and memory in deferred rendering, there is a lot of data stored per pixel, usually more than 64 bytes per pixel, so the gbuffer becomes very large. In forward rendering, there is no such problem because lighting is calculated directly per object and no large gbuffers are required. So that's why forward rendering is lighter on memory and bandwidth. You can also combine both methods. For example, use deferred rendering for opaque object, which is obviously by default, and you can use the forward rendering for transparent objects, and this is actually what happens in many engines, including Unreal, of course. In the project settings, you can go to project settings, rendering, and enable forward shading. This forces the engine to switch from deferred, which is the default one, to forward rendering. But remember, this will disable features like Nanite and Lumen, and you can always compare in deferred rendering, try to disable Nanite and Lumen, measure performance, like the milliseconds per frame, then switch to forward rendering and measure performance again, because obviously there is a lot of options that will be disabled in the forward rendering, so you need to disable them in deferred rendering manually, so you can compare the two, of course, the two options, and always compare in the build version, not your engine. And of course, this will help you decide which one is better for your game. That's it for today. See you in the next video.